Now let's proceed to AC steady state circuit analysis. So phasor relationships for circuit elements. For resistors, in the time domain, V is just equivalent to I times R. Now if we convert it to the frequency domain, it's just the same. V equals to I times R. Now graphing the phasors I and V, they are in phase, or there is no angle difference between the voltage and the current. Now for inductors, in the time domain, the voltage across an inductor is given by L di dt. Now in frequency domain, the voltage is j omega times L times the phasor I. Now if you plot the phasors I and V, the angle difference between the voltage and the current is 90 degrees for a purely inductive circuit. And we can say that the current is lagging by 90 degrees from the voltage V. Now for a capacitor, the current is given by, in time domain, is C dV dt. Now in frequency domain, the current is j omega C times the phasor V. Now, if you take a look at the phasor diagram, the voltage and the current is 90 degrees out of phase. But in this case, the current is leading by 90 degrees from the voltage. So our reference is the voltage. So when we say leading, the current is leading the voltage. Or when we say lagging, the current is lagging from the voltage. Now impedance and admittance. So the impedance Z of a circuit is the ratio of the phasor voltage V to the phasor current I. So the impedance is measured in ohms. So for resistor element, in frequency domain, V equals to Ri. So the impedance is just equivalent to R. Now for an inductor, the voltage is V equals to j omega Li. So the impedance, which is the ratio between the voltage and the current, equivalent to j omega L. Then for the capacitor, the frequency domain voltage is I over j omega C, where the impedance is 1 over j omega C. Now the admittance is just the reciprocal of the impedance. So as a complex quantity, the impedance may be expressed in rectangular form. So we have R plus jx. So this is our resistance. And then x is our reactance. So the reactance x may be positive or negative. So when we say that impedance is inductive, when x is positive, or capacitive when x is negative. So when our impedance is, for example, equivalent to R plus jx, this impedance is inductive. But if our impedance is written as R minus jx, this impedance is capacitive. So the impedance, the resistance, and the reactance are all measured in ohms. So their unit is ohms. So the impedance can also be expressed in terms of its polar form. We have Z impedance is just equivalent to the magnitude with angle theta, where the magnitude Z is equivalent to R squared plus X squared. And the angle is equivalent to tangent inverse of X over R. Because if you write this in the phasor diagram, this is an example of an inductive impedance. This is an example of a capacitive impedance, inductive capacitive. We have positive theta and negative theta. We have our R here, and this is our X. This is negative. So looking at the triangle, R is just equivalent to the magnitude Z times cosine of theta, and X is just equivalent to magnitude Z sine of theta. For example, this circuit is operating at omega equal to 10 rad per second. So converting this circuit into time domain, we have negative J100 series with 100. Then we have again negative J100 last branch is J80 series with 200. Find Zin. Now combining impedances is just like combining resistances. So Zin is just equivalent to, we have 200 in series with J80, and it is in parallel with negative J100 plus, so the combination is in series with 100 minus J100. Our Zn is just equivalent to 149.50 minus J195.05 ohms. Or if expressed in polar form, we have 245.76 angle of negative 52.53 degrees ohms. Now for Kirchhoff's laws in the frequency domain, so for example, for KVL, we let V1, V2 up to Vn be the voltages around a closed loop. So applying KVL at that loop, we have V1 plus V2 plus up to the nth voltage equal to 0. Now for example, the voltages are sinusoidal voltages. So we have V1 is equivalent to this voltage, V2 is this voltage, up to the nth voltage. Now using Euler's identity, this expression can be expressed this expression, or factoring out e to the j omega t, we have this line. If we let Vk complex number, Vk as Vmk e to the j theta k, then this equation becomes this one. Then if our e to the j omega t is not equal to 0, so our V1 plus V2 plus up to V sub n is just equal to 0. So we can apply Kirchhoff's laws in linear AC circuits. So the same with the DC circuits. So the same applies with the KCL. So techniques in circuit analysis such as nodal, mesh, superposition, source transformations, and Thevenin's and Norton's theorem can still be used in linear circuits in the frequency domain. So steps to analyze AC circuits. So first, transform the circuit to the phasor or frequency domain. Then solve the problem using circuit techniques. Then third, transform the resulting phasor to the time domain. So first, let's have this example and then apply nodal analysis.